Hello, my name is John Iconis, and in this video we analyze a database compiled by the U.S. Centers for Disease Control. The Youth Risk Behavior Surveillance System polled children from 45 U.S. states, U.S. territories, tribal governments, and the District of Columbia. Respondents answered health-related questions including alcohol, tobacco, dietary, and other behaviors every 2 years since 1991. Respondents are U.S. high school and middle school students between 12 and 18 years of age. We import CDC data and develop classification and regression models. We start off here doing a classification analysis, and then we complete a regression analysis. We analyze using Python and Pandas. Our raw database comprised almost 1 million rows of data arranged in 150 columns. We began wrangling data looking at unique values for each column. My first query revealed that although almost every column had NaN or null entries, there were no unexpected characters or out-of-range data to filter. We formulated a strategy based on best practices and analyzed the NaN fraction of each column. We set a 70% retention threshold, meaning columns exceeding 70% NaN were deleted. These deletions eliminated 30 columns that were mostly null values and kept about 457,000 rows and 61 columns for analysis. For the 2 columns of continuous numeric data, I replaced NaN with the median value, the recommended approach. Most of our data, however, was ordinal, and for ordinal data, I chose proportional replacement. In other words, if 10% of column data was a value, say 5, I replaced 10% of NaN in that column with the value 5, an easy concept. For classification, we examined question Q11. Of girls who texted while driving, on how many days did they text? This graph shows the initial distribution of data. Actually, most people did not text while driving. That's why bars 1 and 2 are so tall. Because we were interested in textures, we dropped these columns. Also, texting was not prevalent until 2009, so we dropped previous year's rows. After this wrangling, our data plotted as shown here. We applied trees, KNN, and logic classifiers with mixed results. Our naive accuracy prediction was 82%. Trees methods varied from 73% to 82%, with the highest accuracy obtained from a boosted tree operating on all 48 data features. KNN produced a 75% accuracy, even though we applied the optimal number of neighbors, which was k equals 23. Logit regression proved our best attempt and returned a highly accurate result. For Logit, data must be further wrangled into binary form, and we show that in an upcoming slide. Next, let's step through our process. This heat map correlates Q11 with all other variables. I generated pairwise correlations and identified the 12 most impactful variables for the first tree analysis. We plotted the first decision tree in a couple of different ways. Here's one. The first tree predicted with 76% accuracy, which was less than the naive result. The workbook shows how we tuned this first tree by allowing more depth and changing other parameters. Although we increased accuracy, the result predictably was overfit. After cross-validation on training data and fitting to test data, our best accuracy was 73%. We next applied bagging, random forest, and boosting methods, and we found that increasing feature size to the entire 48 variable set increased accuracies as shown. This indicates that variable selection methods, stepwise, criterion-based, or other, could be better methods to select input variables. We did use random forest and boosting model importance calculators to display the most impactful variables as shown here. Next, we apply k-nearest neighbors algorithm. It is important to use the optimal number of nearest neighbors. This plot shows that k equals 23 gave the best result, and using 2 different codes, we estimate between 75 and 78% classification accuracy. As a bonus in the workbook, we index those neighbors for each data point. Next, we applied Logit, our last classification method. Our Logit tool uses binary output, so I consolidated our 4-class output into 2. Class 1 now contains girls who texted a lot while driving, and Class 0 contains those who texted not as much. Note that when we binarize the data, our naive estimate changes. We calculate our new naive estimate at 60%, as shown. Our actual versus predicted samples look good, and even after cross-fold training and fitting to test data, the accuracy remained the best achievable. I experimented with the probability cutoff, but really was not able to detune the model. So the cautious researcher wonders if he's developed a near-perfect classifier or if there is more to the story. Anyway, we next plot the gain and lift charts with great results and finish our classification portion. Now we move to regression, where we examine question Q12. During the past 30 days, on how many days did boys carry a weapon such as a gun, knife, or club. This graph shows the initial distribution of data. We find although 38,502 boys carried a weapon 6 or more days last month, most boys do not carry weapons, and that's again why bar 1 is so tall. I'm interested in weapons carriers, so I drop bar 1. After additional wrangling, our data is plotted as shown here. There are about 50,000 boys that carried weapons. We applied linear and decision tree regression tools. Linear regressions did return RMSE values, of course, but we found linear models did not map well to ordinal survey data. Trees methods return similar RMSE values as we discussed below. Next, let's step through our process. We found important variables by pairwise correlation. Again, we might have benefited by applying a variable selection method. I plotted a few important pairs just to highlight the granularity of ordinal data. I fit a linear regression model using 12 independent variables and did not generate a good result. All parameters indicate a poorly performing model. In the workbook, I tried again using all the variables, but did not improve the output enough to make a difference, so we punt on linear regression. Finally, I fit a regression tree with 47 input variables to the boys' data and calculated the root mean square error. To complete the analysis, I applied ensemble trees with similar results. To summarize the study, I found classification methods, especially logic regression, were most suitable for analyzing our ordinal survey data. I found data wrangling to be surprisingly involved, and I was very pleased with all the resources available online to complete Pandas and Python projects. Thank you for watching.